All right. Hello, everyone, and welcome to Ask Professor L. If you have a math problem that you would like to see worked out, I can't promise you I know how to work it, but if I can and I do know how to work it, I'll be happy to do so. That's kind of what this channel is about. So I have prepared a subject that I want to present, and this is about me getting to learn to do the math and get familiar with working with the camera, mainly just because I'm not good with that. So um, being able to think clearly and um, critically about the math while I'm on public um, domain it's not natural for me. So it's good for me to. It's forcing me to do the math, which I really need to be doing, and also hopefully helping somebody out there. So welcome in if you're watching, and I, I'm really glad to have this opportunity to do this. So I'm going to go ahead and continue working with similar triangles. I did one example last time, and I just wasn't really happy with it. So I went and found some more examples. I haven't worked them yet, so we'll just see how it goes. But I'm going to do a little bit more work with the similar triangles. And then after that, I want to revisit the unit circle and again pick up the topic of the trigonometric functions. Excuse me. Okay, so I am going to go ahead and actually erase most of this. And we'll leave out the Pythagorean for now. And let me go ahead and erase all this. I also relearned how to spell isosceles. I messed it up yesterday. No practice here. So an isosceles. I left out the C yesterday, and then today when I was trying to respell it, I put the C up here in the front. So isosceles, he's worthy of me spelling his name correctly. So I think that it's important for me to work through my math and make sure that I'm thorough. And so if I ever do make a mistake and I catch it, I'll try to correct it. I really don't wish I was perfect. So I've learned to embrace my mistakes. Okay, so what I want to do next in similar triangles is talk about this this thing called the geometric mean. So I'll put it here, geometric. I'm gonna back up here. I think to be more organized, we'll just erase Pythagorean. We can put him up here again later when I want to talk more about him. Pythagoras. And what I want to do is I want to try to explain this thing called the geometric mean. So I better title it correctly. And what geometric mean means, what it is it's a proportion, it's a ratio of side lengths, and essentially it's, so if you have A and a height of h, and this distance a, and then b. According to the geometric mean, a over h is equal to h over b. Just like that. So if you have, and I pulled up 2 examples, if you have missing, and one of them that I found, and these are just random examples that I'm finding, my textbooks and my notes that I've saved over the years. So one example, we'll put it right here below it, is this triangle. If I can get an accurate sketch. Trying to not be lazy, and really, it's really good for me to discipline myself to come in here and work on my board and do the math. All right, so this one, area 5, 12, so that's a right angle, and that's a right angle. And then we have X, Y, and Z. And it's asking us to find the missing values, find values for X, Y, and Z. All right, so according to this theorem, since I have A and B known, I should be able to find X pretty well. Should. Since X is the height. Let's see here. What else do I want to do? I wonder if, and honestly, I have not worked this one yet, but I should be able, let's see what happens. So A would equal 5 in this case, and B is going to equal 12. And then H is X. So according to this, if I put in, and there's other theorems, I just don't have them handy. I don't have them memorized. So I could probably go and relearn these other ones and look them up. But I should be able to say 5 over X is equal to X over 12. And set up the proportion that way. However, when I do this, X times X, when I cross multiply, I'm going to get an X squared. So let's see what happens. So 12 times 5 is 60, I think. It's like, I know the answer, but I don't trust it, so I like to see and double check. So that's probably going to annoy some people if I do end up getting participants. So if I cross multiply this and I get, that's going to give me X squared equals 60. And so then to solve this, X squared, it boils down to inverses. If I want to undo a square, I have to square root it. And then inevitably, when you take the square root of something, you have a positive and negative. However, we'll just take the positive root because of the fact you can't have a negative distance. So I don't know if this is correct. And I don't think that this problem gave me the solution. So hopefully that this is correct. And I guess if it's not, hopefully maybe someone would let me know. So I'll say plus radical 60 for x and put radical 60 there. I think that I'll probably go ahead and take the time to reduce radical 60. Let's see if I can. Reducing radicals, so rules for radicals, maybe we'll cover that one day, but that is going to be, you just start splitting it up into its prime numbers and see if you can get real roots. So that's 6 times 10, and then so that's 3 times 2 times 2 times 5. So really I'm just pulling out, what was that, 2 radical 15 for x. And then, so we've got x, and I'm going to replace that. Where's my good eraser? Well, it's 2 radical 15. Maybe next time I should go ahead and work it out early. But I really don't want to do that because part of the reason why I'm doing this live stream is so that I'm putting myself out there so that I'm working with my board in my math. So I'd rather just get comfortable in this space, if that makes sense. Okay, so we have x, and then we need to figure out y and z. So I erased Pythagoras up here, but I really feel like I need to put him back in here now. So I went back and read about the unit circle and history of math. And while I'm putting this triangle in here, we'll go ahead and talk about it. It was Hippocrates and ancient Greece and Pythagoras. And as I suspected, I was correct. The unit circle, there's evidence that the ancient Babylon society, long time ago, they were base 60 numeration system, and ancient I think it's, yeah, the Babylons, they had the ancient or base 60, and so then they had the unit circle already split up into 360 degrees. So Pythagoras probably studied math in depth, and he's the one that popularized it. Like, he had followers. Anyway, so for right triangles, you have a squared plus b squared equals c squared. And a and b are the legs, and c is the hypotenuse. So the anatomy of a triangle, you have the big uppercase letters that signify your vertexes, your angles, and then you have the little lowercase that signifies the side length, and that's the notation for the math so that we keep all of our values straight. The legs are interchangeable because of this addition property. It's commutative. But the C has got to be by itself on the other side of the equal sign. It's like A and B, see your way out kind of thing, where it's very specific. A and B go together and they have a positive relationship, and then C is the outcast. It's got to be over here on the equal sign. So it's kind of a big deal. But A and B and the triangles, you'll sometimes see A down here and B up here, and you'll see other letters used, but the relationship is always going to be the same between these values. So I should be able to add up the squares of the side lengths, and they should be equal to the square of the hypotenuse. And the proof of the Pythagorean theorem is pretty cool for me because I like math. But maybe one day when I run out of things to talk about, we'll do the really quick proof of that using actual squares in geometry. So when you square something, you're initially you're finding the area of a square. Okay, so we're going to use the Pythagorean theorem. I think that would be the easiest thing to do to find these missing values. And if you notice, maybe I should switch colors, or just, you could split this triangle up. It would help you see it better, but you have this smaller one, the smaller triangle, and you got your right angle here, and it's saying that one leg is 5. Maybe I draw that a little bit bigger. Hang on. I could do that. Got that smaller one, and that's a right angle. And it's saying that's 5, and that's 2 radical 15. And you're finding y. Then essentially your A is going to be, would be 5. You'd say A equals 5, B equals 2 radical 15, and then C, I don't know what C is. C is my hypotenuse, it's Y. And then you just plug in your form, 5 squared plus 2 radical 15 squared equals y squared. And then 5 squared is 25. And then to figure this one out, we have to square both values. So 2 squared is 4. And what that means is 2 times radical 15. So you'd say 4 times. And then 15 squared, when you square something that's under a radical, remember those are inverse operations. Initially, one undoes the other. It returns you whatever is inside of it. And 15's there, so it would be 4 times 15, and that equals y squared. And then 4 times 15, is that 60? Yeah, so I already know. I'm already starting to get comfortable because one of the signs that I'm nervous is that I don't do the best thinking. I have to double check quite a bit when I get. So I'm already getting comfortable, and that's a good sign for me. And so 60 plus 25, that's 85. Y squared. And we'll switch it around because we like to see the variable on the left. I do. And then again, to solve for that, what you do is you take the square root, doing that inverse operation to get whatever is inside there. When I take the square root of y squared, I just get y, and then that's going to equal plus or minus the square root of 85. Anytime you take the square root of something, you get a plus and a minus. Well, y is representing a distance, so you can already trash that negative value. It's no good. So you would just take the positive value. And then dealing with radicals, if I would have worked this problem ahead of time, I would have realized that, and I don't know, maybe I would have still worked it, but I wasn't intending on spending my entire hour talking about radicals and how to simplify them, but I feel like that it might be relevant. So I'll just put it here at the end. I don't want to do that. I'm going to erase anyway, so I might as well just put it up here. So radical 85, what you're doing is you're using the rules for radicals, and everything's staying under the radical, but what you're doing is you're splitting it up into its unique prime factorization. And I'm going to first do that just by the old, the exhaustion method. I don't know if anybody's familiar with the method of exhaustion, but I think it's a real thing. And 80 is just brute force, So I know that it divides 5 evenly, so or 5 divides 85 rather. And that 17. I think that it cannot be simplified. So it's just radical 85 because 85 is 5 times 17. And 5 times 17 is, well, they're both prime numbers. And so there's no duplicates. So the only time you can simplify a radical is when you have perfect copies of numbers. And since there's not one, it's just a 5 and a 17. 17's prime. Okay, so this one's good for y, I guess. And then we've got one more value to find, z. We'll just see what we want to do. Well, there's a couple of things that you could do. You could just use this other triangle because it's a right triangle and find z that way, or you could also use the bigger triangle and add 5 plus 12 here for this entire side length. And since I already know y, that's the hypotenuse of this other. So I kind of want to do that. We use the this would be the hypotenuse. So I don't know if you can see this bigger triangle. So I'm going to go ahead and do that. We'll try and draw it exactly. I'll erase this as I see it, as it's there. It's like this. And this was your right angle, so this has to be your hypotenuse. And that was 5 plus 12. That's 17. And then we said that y was, this side here was square root of 85. What is the square root of 85? Does that even seem plausible? I wonder. Yeah, I guess. Hang on. Square root of 85. Okay, so if I squared it, okay. Or let's just try it, see what happens. All right, so we have the square root of 85. So according to my Pythagorean theorem here, I have a equals, we'll call that the square root of 85. B, in this case, is my z value here. So z is going to be unknown. And then we have C, my hypotenuse, is going to be 17. So then we'll plug it into our formula. And we have, I like lists when I'm using formulas because it makes it really clean. It's just plug in and simplify. So little side note there. So A would be A squared, B the square root of 85, quantity squared. In this case, B is Z, so it's plus Z squared. Hopefully I'm not in the way too much. And then we have 17 squared for C squared. All right, so again, when we square a square root, we're going to get 85 back. And we have Z squared, so plus Z squared. And then 17 squared, I don't have that memorized. So let me go ahead and figure out 17 squared. Eventually, when I get really comfortable and good with all this technology, I would like to have a document camera on my calculator so I can show you all how to use the calculator. 289 is what I'm getting. And then we'll have to solve this for Z here. So what we'll do is using the properties of real numbers, the property of equality, and this one will be subtraction. So when you're solving an equation, you can perform any mathematical operation that you want to solve it. You just have to make sure that you're obeying the equal sign. So it's you have to do unto one side, you have to do to the other. So it's the exact operation. So what I want to do is I want to isolate Z. I want Z by itself on one side of the equal sign, and then I want everything else on the other side. So I want to do that in this as a few little steps as possible. So the first thing that I see to do is to subtract 85 from both sides. So that's what I do. So minus 85 and minus 85. And then those cancel out. They're additive inverses. So that gives me Z squared by itself there. And then I have to figure out what 289 minus 85 is. And I'm getting 204. So I would, to solve for Z, I'll have to take the square root of both sides. Again, positive and negative, 204. And then I'm going to ignore that negative because I'm talking about a distance. And you can't have negative distance. 204. And so let's see if we can reduce that one. It's good practice, and someone maybe will watch this video, not know how to do it, and learn how to do it. All right, so 204 is even number, so it's going to divide 2 for sure. Use the old exhaustive method, and that's nice because, let's see if I can write sideways in that room. 102 times 2. Maybe we should just do a factor tree first. But it also is divisible by 2. And that's got, what's that, 51 times 2? Yeah. So we got 51 times 2 times 2. So that perfect root can pull out. And I'm wondering, I think 51 might be prime. So that's going to be 2 radical 51. And I want to see, I'm pretty sure it's prime. No, it divides 3, but it's 3 times 17, and I think 17 is prime, so we won't be able to reduce it down anymore. So it's 2 radical 17 times 3, and then those are both prime, so we'll just leave it here. And wow, that took a lot longer than I thought it would. The other example that I was wanting to work for similar triangles, we'll see how long it takes. If it takes, see, I've been live for 30 minutes. And if it takes 30 minutes, I'm hoping it won't. What I'll do is I will start the trigonometric functions, what I wanted to talk about next time. So we'll go ahead and work one more example of similar triangles. It's very necessary for what we have to do to solve more advanced trig problems. So I kind of want to work my way that direction. All right, so let me go ahead and erase on this. All right. That one. Where's that other example I have? Oh yeah, it was involving the special triangles, which that's what I was wanting to do. This one also, I was not smart and I didn't figure out the answer first, but that's okay. So it says, okay, similar triangles. Oh, this squeaky marker, I don't know. I never noticed it before I did camera, but it is a problem. Try not to squeak the marker, it bothers me. All right, this one. That does not look. Okay, so And it's not an accurate sketch. Because it's not a scaling. This is an isosceles. So make sure I draw it to look like isosceles. Let's see. That's a that looks like an what is rule? Let me try one more time. Hang on. All right. There has to be, there you go. Okay, it has to be a right angle, and we're just gonna have to say that that's 45, because I don't want to sit and waste 10 minutes trying to draw a triangle. 3, y, and x, and then we have so if I wasn't trying to draw an isosceles, I would have no problem drawing it. But the fact that I'm trying is making it harder. All right, so I just need to relax. And maybe just pretend like the camera's not there. I don't know. Okay. And so this one, they tell us all three sides, 9, 12, and 15. And we're going to find x and y. And I want to star this problem and later on go back and use trig to find it. But for now, we'll just use the fact that triangles are similar and set up a proportion. So since we have a similarity, and we can prove similarity because we have an angle, we have two angles known, and we have two angles, then that third angle is fated to be congruent. So I can say that 3 is to 9 as x is to 15. And set up a proportion that way. As long as you're consistent, if you start with the smaller triangle in the numerator, you want to have the smaller triangle values in the numerator on the other side of your proportion. So we'll say, if we want to find x first, we'll say 3 is to x as 9 is to 15. And then you'll just do your cross multiplication. And so you end up with 9x equals 15 times 3 is 45. And then you would just divide off the 9, and we get x equals 5. And then at this point, you could, if you wanted to, if you, wait, it's not going to be, it's not an isosceles. How is that possible? And maybe I'm overthinking this problem, but it said the angle was right. Okay, I can't assume. All right, so I don't want to make this more than it is. It's not an isosceles, and because I can't assume that that's a right angle, it's not in the problem, so I have to make sure that I'm doing this correctly. So I'm not gonna put that in there, because what if it's not a right angle? It's not saying similar triangles. This is good for all triangles. It's not, I mean, I am moving in the direction of presenting, in reference to special triangles and right triangles, but it's worth stating that it's good for triangles that are not right also. So you can still use this proportion. Doesn't have to be. That's just me being out of discipline, I guess. I gotta be careful. So go ahead and leave it like that, because I'm not sure if those are right, and in the diagram it's not there. So all right, moving along. X is 5. And if I can't use Pythagorean, wish I could, and I was thinking I wanted to, just because I want to practice working with it, but since that's not given right, triangle right angled, I can't use Pythagorean. We'll go ahead and just set up another proportion to find this other missing side. So we'll say y is to 12 as, we'll go ahead and use the values that were given, as 3 is to 9. And then just really, we'll go ahead and work this out the long way. I did this before. This time we'll go ahead and do it the long way. Just proving that this works. If you don't remember how to do this, when you're solving for y, you're still performing inverses. And so what this means is y over 12 means 1/12 times y. And so you find the reciprocal whenever you have a fraction. And so you have to remember reciprocals. So reciprocals have, so every number has a reciprocal. And the product of a number and its reciprocal is 1. So that's how you find it. Anything divided by itself. So 1 times 12 is 12, and 12 times 1 is 12, and then that's just 1. So to solve this one, I'm just going to multiply both sides by the quantity 12. And those are going to cancel. So it'll be y equals 3/9 times 12. Well, you can just put 12 over 1 and multiply. And so you get 3 times 12 is 24, 36. And 9 times 1 is 9. And then you just simplify by dividing. 36 divided by 9 is 4. So this one is one of those 3, 4, 5 triangles. And that this triangle is from ancient Babylonian and Egyptian society. I know that I remember learning about the 3, 4, 5 ratio, but it can't be. It's saying that it's a 45-degree angle, but I'm struggling with that, so I'm gonna have to process it. I don't know, but we found the missing side length. It could be a bad problem. I've noticed like AI generated problems. They give you the most popular, sometimes not the correct. But This one wasn't from AI. Where did I get this one? Okay. So there is another application of similar triangles. And let's see. Okay, let's see what else I wanted to do today. I've got about 15 minutes. Maybe I should go, oh, do I have one that estimates the height? Let me see. If I do, I'll go ahead and work that one. The height. All right, let's go ahead and do it. Just to stay on the subject, since I only have about 15 minutes left in my time, what I want to do is I'll go ahead and work one more. One of my favorite applications of similar triangles is like estimating the height of something that's really tall, a tree or something, just using shadows, and you literally stick a pole in the ground and you measure the shadow and you measure the pole and you set up a proportion. It's pretty cool. So this one is similar to that. And it's also not, this is good practice for me. So even if I don't have any listeners or any followers or participants at first, it's okay, because it's so good for me to do this math. At 5, 10, 15. And this one is 10, 20, and X. And again, we don't know if it's a right triangle or not. Let me see, how do I know it's proportional though? Oh, okay. So if you can find a K constant, let's test for proportionality. Oh, wait. Hang on a second. We have I'm going to assume they're similar. Because what if I think they have 2 side lengths, this relationship. So yes, no known angles. Okay, all right. So this is not a good problem. It's not the one I want to do. It's okay. We'll do it anyway. So I have 5. We'll do 5 is to 15 as 10 is to X. 5 is to 15 as 10 is to X. Okay, and see what happens. So that will be 5X, and then 15 times 10 is 150. And then just divide off 5. And how many times is 5? 30 times? X equals 30. Does that seem... Oh, well, we just made them proportional. So X would be the value that makes them proportional. Okay, interesting. All right. So what I think I will do is I might go ahead and stop on the math there, um, and pick it up again tomorrow, and we'll talk about the trig functions, and I'll put the definitions in. Use the unit circle again tomorrow, and I think we'll call it good for today. That was a good little learning moment for me. But I realize sometimes it's good to know what you don't know. And all right, so we'll call it good. And I appreciate any comments, that suggestions that people have for me to help me to improve on my presentation for you. And all right, so thank you, and I hope that everybody has a good rest of their evening.